Good morning, almost noon, everybody. Maybe noon for some of you, depending on where you're calling in from. Thanks for joining us today for getting started with .NET for with AI for .NET for developers. We're really excited to have you here. I'm glad we're getting to do this today. My name is Christina Colson. I'm the AI strategy lead here at Lean Techniques. And if you want to go to the next one, Dan. Just a couple of words about LT, in case you're unfamiliar. So we're a technology and management consulting company based in Iowa, and we have a bunch of people working remotely across the US. I'm in Colorado, for example. At LT, we help organizations turn technology into a competitive advantage. And to do that, we work with leaders and teams to build skills across 5 areas that you see listed here. So we do software delivery, cloud, product management and design, leadership and strategy, and of course AI, which we'll be digging into together today a little bit more. We are a Microsoft partner and have 3 Microsoft Most Valuable Professionals or MVPs on our team, including Dan, who will be presenting today. And then if you want to move to the next one. Basically, that's it to get started. So as we go through today's session, we're happy to make this a little bit interactive. So feel free to pop questions into the chat and I'll keep an eye out for those. And we'll try to address them along the way. And then we should also have a little bit of time for Q&A at the end. So with that, I'm excited to introduce Daniel Ward, who is a professional software consultant here at Lean Techniques and also a Microsoft MVP. So Daniel, take it away from here.
Cool. All right. Thanks, Christina. Yeah, like you said, we got people all over. So I'm based in Texas, San Antonio. So thankfully, same time zone as Des Moines, which I assume is where most of y'all are coming from. So anyway, like Christina said, this is getting started with AI for .NET devs. This talk will kind of be chopped up into 2 parts. So what are the goals of this talk? Why am I doing this? Basically, the reason I made this talk in the first place is for myself. I didn't know kind of a lot what was going on with AI. I knew like how to use it myself, how to use ChatGPT, GitHub Copilot, that kind of stuff. But whenever people at work started talking about stuff like, RAG and fine tuning and tokens, I didn't really know any of this stuff was, and I didn't know how to talk about it. And for some reason, it felt like everybody else somehow knew what this stuff was, except me. So this is kind of just to explain under the covers a little bit how AI and LLMs work and what do those things even mean. And even if we don't make those things ourselves, we're not making the LLMs. I think whatever level you work at, it's always helpful to know a little bit one level deeper. Take away one level of abstraction, and I think that helps a little bit with your own work. So yeah, like I said, just kind of high level picture of what AI looks like today. This will be chopped up kind of into 2 parts. First part is the theory, which is kind of just what I talked about, going over what all these terms mean, kind of how LLMs work in general. And the second part, the for .NET devs part, will be going over Semantic Kernel. So what is Semantic Kernel? Be a little coding demo, how to use Semantic Kernel, see it in action, be kind of cool. So really, I only have 2 goals for this talk. One, obviously, know about Semantic Kernel and be able to use it. But also, 2, just be able to speak at least semi-intelligently about AI. When people in the same room are talking about it, you're not completely clueless. That was my goal when learning about this stuff. And honestly, quite a lot of research went into this, and I'm condensing this a lot. So probably 20 plus hours of reading and watching videos and stuff. And all that to say, you can go super deep into this stuff if you want to. That basically all the topics I'm going to talk about, I'm going to really scratch the surface. So I'm going to try to keep it about 20 minutes on each of these sections. We'll see how I do. Okay, real quick. Like I said, this talk won't be in depth on anything I go through just because time constraints, and also I don't want your eyes to glaze over about the math of how all this stuff works. There is a bunch of philosophy really about how we should use AI. I won't really be going into that related kind of morals and ethics. I think I have literally one slide about this, but whenever we talk about how AI works under the covers, these questions always seem to come up. I won't be talking about that stuff, not because I don't care about it, but because I don't have time to go over everything. So, real quick about me, like Christina said, I'm a developer and a consultant here at Lean Techniques. I'm a staff engineer here. I'm a Microsoft MVP in developer technologies. I co-organize the .NET user group down here. And you can find me all these places online. Really, the important one here is danindacan.com, my .NET blog, because you can find all my socials and everything on there. So please do add me on socials if you found me from this, if you think it was cool, if you have feedback, if you thought the talk sucked really bad and you want to message me and tell me that, uh, please do that. It would be cool to find people that found me from stuff like this. So, okay. To start off, what in the world is AI? Because AI is not new, right? I at least have heard the term AI pretty much my whole life in different contexts. So, like, what does that mean? And what does it mean now when we hear AI? So, in general, all AI means is a computer simulating human intelligence. That's it. Okay. AI itself does not imply machine learning, chat GPT like intelligence, any of that. Okay. So, like, it's not new. It's been around since at least the 50s when the Turing test was invented. As an example here, let's take video games because this is what I thought of. So this is a behavior tree in Unreal Engine. So what I thought is, I heard that term AI basically my whole life from video games. You talk about enemies having their own AI, like the AI is acting like this. So that's still AI. What's the difference between AI and AI we have now, right? So you can see in the example here, the tree, if they have line of sight of the player, they chase the player, and then depending on where they are, they might rotate or they might run, and then otherwise they just patrol or wait. In which case their movement is different. So this is still AI, right? It is. It's simulating human intelligence at some level. It's making decisions about how it should act, and presumably, if it's like an FPS or something, it's going to look like simulating a human behavior. It's going to be walking around a hallway, it's going to chase you or dive out of the way if you shoot at him or something, right? So this is still AI, but we kind of get the idea that this is not what people mean when they talk about AI nowadays, right? So this kind of started with the Turing test. I put 1950, I think it was actually 1949, but Alan Turing made this thing. He said, AI should be able to, the Turing test is you print out just an English conversation between a human and a computer, and you give this conversation to another human. And if that human cannot tell who's the human and who's the computer, then it has passed the Turing test. So this is still the goal. Okay. This is still what we're trying to, this has not changed. This is still what we're trying to accomplish. We've just gotten a lot better at it. And even back in the 50s and 60s, we had computers that were learning how to play checkers and solve algebra word problems and respond in English. And we had neural networks, which are still what modern AI run off of. So kind of like we had all this literally decades ago. So what happened recently that this kind of exploded, right? In 2010s, all of a sudden we have machine learning and deep learning. And then late 2010s, Chat GPT came out, right? We have these things called LLMs and transformers and generative AI. So we had this massive boom that we're still in. So what happened there? And what are the important bits out of that? So I'm going to start with this. This picture is supposed to illustrate me when I was first hearing these terms, supposedly all being used as synonyms, but with AI and machine learning and deep learning and generative AI, and are these the same things, and how are they used colloquially, things like that. So really, it's simpler than you might think. They're kind of just subsets of each other. Like I said, AI is the whole field, right? And that's not new. It's been around for decades. You're just trying to get computer to act like a human. Machine learning is a subset of AI that allows the computer to improve as it does stuff without you, the human, doing deterministic programming and improving it, right? And deep learning is just a subset of machine learning. Basically, the difference is scale. When you do a ton of stuff, all of a sudden it's deep learning. Okay. So neural networks. What's a neural network? This is the thing I said was invented way back in the 50s and 60s. And it is still how modern AI functions. AI is a neural network. So what does that mean? So it's called a neural network because it is loosely based on our own neurons. We have synapses and dendrites and that kind of stuff. And it was modeled after that. So the idea is we have three what's called layers. We have this first one on the left, the input layer. And then we have this one on the very right, the output layer. And then we have n number of hidden layers here. Hidden is where all the magic happens, basically. Input just takes a number, output just spits out a number. Hidden does all the stuff. And you might have thousands, millions of hidden layers, okay? So all this does is math, okay? It's literally, it's only numbers in here. So how exactly this functions, I'm not going to talk about because this is literally a whole nother field of study. You can get a degree for this kind of stuff. If you want to go and look up how this stuff works, that's cool. But it's not, I would not call it computer science. I would call it something different. Okay. So we say the more hidden layers a neural network has, the deeper that network is. Okay. So we have deep learning, we have these deep networks, right? And we have this, if you've heard of weights and biases, we have this function here, just very in general. The output of a node is going to be equal to all the inputs it gets multiplied by the weights plus a static bias, okay? And I'll talk more about this, what these are. Basically, you see all these little relationships between the neurons. We have neurons connecting to a bunch of other neurons. And as sort of it learns, it tries to do stuff and it says, oh, I got it wrong, or I got it right. It strengthens these connections, okay, or weakens them, right? And just like your real neurons have sort of this activation potential, which says, I need this certain amount of energy to activate. I'm either on or off. I'm not in between. It's the same with these, okay? So if you have a high bias, for instance, that's just a static number that gets added to it. That means it's easier for this node to activate, even with a lower amount of weight or input or something. Okay, all this to say, this plays into how the neural network learns once it's inundated with a ton of data. Okay, so the important thing to take away from this is that weights are basically the strength of the relationship between nodes. Bias makes it easier to turn a node on. Okay. So even if it has low inputs, it'll be easier to turn it. Okay. We'll explain a little bit more about that. I'm not going to talk too much about machine learning versus deep learning. Like I said, basically, the difference is scale. Okay. So machine learning is a subset of AI. Using neural networks, it can improve over time on its own without human intervention. So you don't hard code all these rules. You train models to recognize patterns with tons of data, and it gets better at recognizing those patterns. Essentially, deep learning, you add a ton of hidden layers. Okay, use tons of hidden layers, use tons of data. All of a sudden, you've got deep learning. So colloquially, you might just hear these used interchangeably. You know, companies love tweeting stuff like deep learning. It sounds serious and marketable. So, okay. So that kind of leads us to this next thing, which is, okay, cool. We give it a ton of data. It does math stuff. How is it possible that it does stuff like noticing patterns we haven't, or creating new patterns even, right? How is this possible? So if anyone remembers these things from 1 or 2 years ago, AI successfully detected cancer cells in patients. That not only that, it was cancer cells that doctors missed. Okay, and not only that, I believe this particular study it didn't miss any. It didn't get any wrong. Everything that it said was cancer cells, it was correct on when doctors went back and reviewed. And this other one, Google DeepMind, there's some old math problem that humans haven't solved, and it was able to do it. So how is that possible that it can see these patterns and connections that we can't even see? We haven't ever done in history. Like we didn't feed it that stuff. So that brings us to generative AI. So this is a subset of AI, a specific kind of AI that generates new content. Okay, it uses machine learning, deep learning to actually create new stuff. So this is what you're seeing when you use Chat GPT and Copilot, stuff like that. So in order to do this, it needs a absolute ton of pre-trained knowledge and data to access. This is what happened um, probably late 2010s when companies could just find all the data they could beg, borrow, and steal and put it into these models. Things like books and websites, all that stuff they could find from basically all of human history. So LLMs are neural networks, okay? They are just massive neural networks that were given a massive amount of data. All right. So, kind of the special thing about LLMs, large language models, is that they can process, like the name says, natural language, right? So, instead of just having the data there, you can now access that data by typing to it in English or Spanish or whatever, right? And it will respond to you in English because not only does it understand its data, it understands your language and it can respond to you in that as well. So here's Microsoft's image of a neural network, but you can see it's basically the same thing. It is a neural network, right? Now it just has the knowledge of how to respond to you as well, which is kind of game changing, right? That's how we interact. That's how we interface with them. So if you ever GPT, this is generative pre-trained transformer. So break that down. Generative, because like we just said, it generates new stuff, right? Pre-trained, we'll go over this, but it goes through a bunch of pre-training, taking who knows how many petabytes or more of data. And transformer, I think this is not a great name for it, but a transformer is a specific type of LLM because of how it does its math stuff, basically. So it takes a bunch of input and transforms that into a bunch of output. This is a short explanation. So GPTs are just a kind of LLM. Okay. So you're kind of finding out that either a lot of these terms are interchangeable or a lot of these terms are just subsets of each other. Okay. And all a GPT does is it takes in tokens as input and gives you back one token as output. Okay. We'll see how this works. This is what you're doing when you use Chat GPT or Copilot. It's kind of mind blowing, but it's just giving you one new thing at a time. So, really, the two questions I think this is all kind of leading up to, I haven't really answered yet, is one, how does it understand what we ask it and respond accordingly? And two, how does it refer back to its own knowledge to do that? Right? It has just like almost the entire knowledge of human history. How does it refer back to that and spit out what you want? So the answer, at least in part, is this thing called tokens. So this is the building blocks of your input, you can kind of call it. Here's a free tool OpenAI provides called the tokenizer. This is just showing you when you type a prompt to Chat GPT, this is how it ends up getting sent to the AI. It shows you how it gets chopped up. So if I type the English language is sometimes incomprehensible, in this case, that got chopped up into 9 tokens. So you can see, it's not a word, but it's more than letters. So like in this case, most of them were whole words with the space, but incomprehensible got chopped up into 3 tokens. And the period got its own token, right? So a token is kind of this thing that's like between a character, but it's less than a word, right? And that is on purpose. So the idea of a token is to give context, basically, to the LLM of what you're asking. So you could use words or characters; those would still work, okay? But they have their own problems. So if we did whole words, for instance, tokens are whole words all the time, then the problem with that is the English language this week, for instance, is going to be different. It's going to be outdated from the English language next week because we're always getting new slang. We're always getting like a little different suffix on the end of an existing word or different jargon, right? It's constantly being updated. And the way these work is that the model has to keep a complete list of all the possible tokens it could receive. So this is a big list. It's like 50,000 items or something, but it has to keep that stored in memory to refer back to. So that would not be possible, really. Or they have to be constantly updating the model literally every day. It's just not practical. So they could also do on the other side of the spectrum, they could do characters as tokens, right? That would work, but number one, the processing for that would be insanely expensive because each one of these tokens is processed on its own. And number two, there's not a whole lot of context in a single character. In fact, there's almost none. So the word language, you get an idea of from all the other tokens in this sentence how this is being used. Just the letter L tells you almost nothing. You have to take it with all these other characters, right? So tokens is kind of this happy middle ground that still gives us context, right? We can take a suffix or a prefix of a word as context as a token, and with that, we can still keep up with the new words being invented for the most part, and it gives us a good amount of context. So, how these are chopped up, I don't know. I don't care, but they're chopped up into tokens and sent to the AI. And all the AI does, actually, we'll see this, is return you one new token at a time with the tokens you give it. Okay, so how does it do that? So like I said earlier, neural networks don't know about your English. All they know about is math, okay? All they do is math. It's a ton of math. So how that works is these tokens that I showed you on the previous screen, these tokens are turned into, or it's called embedded, they are turned into vectors. And if you remember, elementary school, high school math, these are the same vectors. If you picture XY space, right? That's a vector. It has a direction and it has a magnitude. So it's just a mathematical representation of the data. So here's an example. The word king, it gets turned into this big long vector. So the difference here between the vectors you're probably familiar with in math class is that all the vectors we interact with in life are 2 or 3 dimensional because that's the world is 3 dimensional, right? So you have XY space and you have a vector that looks like that or something, right? Well, these are the exact same mathematical concept, but the vectors that LLMs deal with, instead of being 2 or 3 dimensional, are more like 10 or 20,000 dimensions. Okay. So we have really no way of picturing that. But the idea is each one of these values in the vector has some semantic meaning. It's called a feature sometimes. So in this 20,000 dimensional space that the LLM has, apple and orange, these tokens will be relatively close together, and apple and car will be relatively far apart, right? So each one of these, for taking the example of king, one of these values in the vector might be a value of royalness or a value of kingness, right? Or maybe a value of being hundreds, like medieval history or something. It might have a feature for that, right? Just kind of how it's learned as it's taken in all this data. So as an example, GPT-3, which is old at this point, had about 12,000 dimensions. I could not find any public information on current stuff, but if that's what 3 had, I think 5 is coming out soon now even. I assume these are just way more, right? So here's an example. So here's some tokens. We have woof, bovine buddies say, and moo, things about animals and the noises they make, right? And relatively, they're all grouped closely together. What cats say is grouped closely to meow. Same with dogs and cows. But something completely unrelated, quarterback throwing a football, is pretty far away, right? And the LLM doesn't really know about your English, but it knows these things aren't related. So it's probably not deterministically, probably not going to give you an answer related to this. Okay, when you ask about this stuff. So here's same kind of idea, just in 3D space. This is kind of a cool little tool. If you go to this website, you can even like rotate it in the browser and hover over these dots. But basically, these are kind of groups of information, right? So the orange ones are animals, type of information. Green is athletes, villages, transportation, and film. And you can see kind of in the 3D space, they're close together, right? When they're related. So you can imagine how this balloons out and explodes when you have 5 digits of dimensions. Going just from 2 to 3, it looks quite a bit more complicated, in my opinion, and how mind-boggling it is when you get bigger. So uh, to summarize that, AI does not understand your words. It doesn't even really understand your whole sentence. It understands tokens that get turned into big, huge vectors. And it does a bunch of math on the vectors and the neural network nodes. So it's we'll go into the training on an I think in a couple slides. But basically, it says, "Oh, that answer was wrong. Okay, I'm going to make that weight a little less, and I'm going to try again in the future." And over time, if you give it enough data, it'll get pretty accurate with where these things should be in space. Okay, so I want to point out again, we had a bunch of this stuff already before 2017 when LLMs and stuff exploded. Okay, we had the math for decades. This stuff was not new. What was new was this thing called attention or attention blocks. This was a paper that Google published in 2017. And actually, they were not even trying to do this whole AI revolution thing. They were trying to make something that could translate, like from English to Spanish or something, a lot better. That's what they were trying to do. So it is related, they made something that can understand language. But they invented this thing called the attention block with neural networks. And it's not important that you understand how the math of this stuff works, but it did two main things that were new for neural networks, which it allowed all these massive amounts of tokens and nodes you have in the neural network. It allowed each token to consider all the other tokens in the context, not just the ones before it. Okay. So they call it attending. Each token can attend to other tokens and get context. So in that sentence, the English language is sometimes incomprehensible. Language can look at all the other tokens in that sentence to get context of what language means there. Okay, so that was new and it was a big deal. The other thing that was a big deal is that each token did not have to wait on all the other tokens to be calculated before it. They could all be calculated at the same time in parallel. And that is huge. It sounds like not interesting and small. You can calculate in parallel now. Cool. But we're doing just massive amounts of math here. So, one, allowing for parallel calculation, and two, the modern amount of cloud computing hardware we have now allows for this massive explosion to happen, right? So, as an example, if I ask LLM, what is the capital of France? Something that's going to look for semantic meaning for, right? This is kind of more complicated than it looks at first glance. You don't have to think about it because your human brain is very smart and good at this. But let's take the word capital. Capital can mean a lot of stuff, right? We can have capital punishment. We can have capital letters. We can have capital gains tax. And we can have the capital of a place, which is what we actually want here, right? And the LLM does have knowledge about all this stuff if it was in its training data, right? So it's going to see, okay, capital. All right, France is in here too. It's asking about capital of something, right? So it's going to get the idea you're probably going in this direction, right? So just because you wrote capital, it's going to be able to figure it out, right? But this is kind of the idea behind the semantic meaning. So if you remember that vector space, right, you're going to end up with something closer in this right side of here, this direction, than the other stuff. So it's going to lean towards that direction. It's just math where what it's closer to in space, what it's more closely related to. So context, all this means is that the LLM keeps a certain amount of tokens that you have given it in memory. It can't do this forever. It has something called a context window because we just don't have infinite amount of memory and storage. And this scales quadratically. So you're keeping a matrix, basically a table of tokens. So if you have 1,000 tokens, that's actually a 1,000 by 1,000 table it has to keep track of. And that's a million vectors with 50,000 dimensions each or whatever, right? So if you scale that up to 10,000 tokens, all of a sudden we have 100 million vectors 100,000 tokens is 10 billion vectors we have to now store. So I think ChatGPT, Claude, these modern LLMs, someone correct me in the chat if I'm wrong. I think they keep around like 7,000 tokens nowadays, around there. So it's just a massive amount of processing and RAM that we need, how it scales. All these vectors and math equations and storage is also why GPUs are so popular right now. GPUs are made for graphics processing, right? Video games and stuff like that. Well, what video games do is vector math. It's physics that are being done in 2D or 3D space. So it's very good at vector math and it's very good at parallel processing, which is just so happens exactly what we need for LLMs as well. Okay, so training. Let's go to training. How we sort of have this idea of, okay, LLMs just use vectors and they see what's more closely related, but how does it get that stuff in the first place, right? How does it get its knowledge, sort of? So to train an LLM, you have two phases. One is called pre-training, which is where you give it this massive data set. You take all the books you can find, you take Wikipedia, all the stuff you can find on the internet, whatever. You take anything you can find, embed it into vectors, right? And then it does all this stuff and it finds relationships between them, and you get what's called a base model from this. And the knowledge is there, but it's not really usable at this point. It doesn't talk in English very well, and the responses are kind of weird. So then the second phase is post-training or fine-tuning. You might hear these used interchangeably. Really, fine-tuning is just one type of post-training, but this step requires at least some manual intervention by humans. So checking myself on time here. Okay, we'll swap over to the coding demo soon. Basically, in the example of fine-tuning, you hire a bunch of people and tell them to make 100,000 examples of basically Q&A. If the model gets this prompt, this should be its answer. And then the model goes through all these curated things and sees if it got it right or wrong. If it got it wrong, it adjusts its weights and biases based on that. And it also kind of gets the tone of its responses. So you also kind of hear people complaining a lot about ChatGPT being too agreeable or something, right? So that might be because maybe in post-training, whoever wrote those things were very like that in their how they decided to write their responses. Anyway, from this you get an assistant model, and all these things make up the model. Okay, this is also sometimes called the foundation model, if you've heard of that. It's just a model that was trained on a massive amount of data that has general knowledge about everything. It's not specially trained on any one thing, really. So here's an example of OLLAMA. So pre-training, get about 10 terabytes of text from the internet, use 6,000 GPUs, about $2 million in 12 days to process all of that into vectors. And you get, some rough semantic meaning, not really refined. And then the post-training, you write these instructions for humans to do. You hire a bunch of people. And like I said, about 100,000 high quality ideas, right? And then you use that to really refine the model. And Christina put in chat has a 500,000 token context window, which is kind of mind blowing to me. Okay, so parameters. If you've heard about parameters, all that means is the weights and biases. It's the strength of these connections, how it decided to form those when it was going through pre-training and post-training and all that. So a lot of times when a new version of like OpenAI or something is released, they'll say, now it has this many parameters. So GPT-4, supposedly, I saw a bunch of places online saying this. I didn't find it in any official sources. GPT-4 supposedly has 1.7 trillion parameters. So that means relationships between the neural network nodes, okay? Practically, what it means is marketing speak to say our LLM is smarter and more powerful now. Use ours. So as the model trains, these parameters get tweaked. They're sort of like knobs you can turn to make it care more or less about a certain thing and change those relationships. So let's take a practical example of ChatGPT. This is something I actually asked it. Said, write me a haiku about C#, and it gave me this beautiful brackets hold the flow, link dances with sharp logic, types bloom strong and bold. So how did we get there, right? Pulling all this together. Write me a haiku about C#. It's transformed into these tokens. I put it into the tokenizer and got this. Practically behind the scenes, they probably did something like this. They gave it what's called a system prompt, which is kind of the role and the tone they want it to have. So, I'm sure the system prompt that ChatGPT has is massive and a lot bigger than this one sentence. But system, you are a helpful assistant willing to help users with a variety of tasks. And then here comes my prompt. And then this actually should not say system. On the third one, it should say assistant. Assistant is the response that now gives you. But it spit out these tokens. And how it worked is it did not spit out these tokens all at once. It spit out these tokens one at a time, like this. So I gave it this user prompt, right? Write me a haiku about C#. It took that into context and said, hey, model, based on all the vectors and stuff you have, what do you think the single next token will probably be? And it gave BR. And then it ran through that whole thing again and said, hey, model, what based on these tokens, what do you think the single next token will probably be? And then it gave brackets. So we have brackets now. And it continually did that until finally we have the whole thing. It is also notable, this is partially random. So they have this thing called temperature, which if you increase it, it increases the randomness. But essentially, if you don't have this, it ends up sounding kind of unnatural and stiff. So in this case, flow was probably pretty high up there compared to these other ones. But basically, it has this table of like possible next tokens that could come and the probability from 0 to 1 that would be the next token. So it does not always choose the highest probability. If there's like some that are close together, it might choose a few ones down, depending on the temperature. But in this case, if flow was 0.8 and these other ones were so small, it's going to choose flow. But it's not deterministic, right? It is a probability of which one would come next. And I want to point out here, this is a good place to say we have who knows how many millions, trillions of nodes in our neural networks. But we're in this spot now where we know the math functions that are running and we know how each node is working, but nobody can tell you how we arrived at the answer for any given question because these systems are so huge. They have so much data and it's just math with some randomness thrown in that nobody can really recreate stuff, or it's extremely hard to really recreate stuff, right? So, okay. RAG, if you've heard of RAG, relatively new. I think it came out in 2020. That is retrieval augmented generation. So you augment the response of an LLM. So the best way to explain what this means is to explain it's only in two phases and what these phases are. One is retrieval. So you say, cool, I have a very general, unspecialized LLM. I want to retrieve proprietary stuff or internal stuff. So I'm going to hook it up to an external knowledge store, and then I'm going to augment my model and generate new stuff based on that augmentation. That's really all it is. So you get improved accuracy if you have internal data, stuff like that, reduced hallucinations, and up-to-date info. Right, you have a model that's trained maybe monthly or weekly, and it won't know stuff that's happened between those points. And then just domain-specific knowledge. MCP is going to be similar. These things overlap a lot, but MCP is a protocol, just like HTTP. It's a protocol that allows your AI to connect to external stuff, to not only read data from it, but interact with it. So you can connect it to Jira to create or finish tickets, connect it to GitHub to create pull requests and stuff like that. I'm going to have to zoom through these next few slides here. Agents, or agentic, which just means an AI is acting like an agent. This is an AI that doesn't just generate tokens, it also creates what's called a plan, and it can decide when to take certain actions for you. So it can do more stuff for you without intervention, basically. So an agent has three parts. Obviously, it's got the LLM. That's basically what it still is under the covers. It's also got state, which is just context that happened, what it's done in the past, essentially. And then tools that it's hooked up to. So these can be deterministic functions that you've programmed. It can be stuff it's hooked up to outside systems. And we'll see this with semantic kernel. So here's an example that Microsoft gives on their docs. The user asks a question. Instead of just going to the LLM now and getting an answer, we can also, do a vector search and go to the cache. And the thing, just the main thing to know about all this is that the LLM is deciding for itself when to do all this with that deterministic programming. We'll see this with the coding demo. Okay, that finally brings us to Semantic Kernel. What is Semantic Kernel? It's an SDK that Microsoft made to build your own AI agents. So it's actually open source, and it's not just for C#. It is also for Java and Python. And it is just kind of an easy to use bridge between an LLM and your code. And again, we'll see this in the coding demo. So the kernel itself, they kind of make this sound more complicated than it is, in my opinion. The kernel is really just a dependency injection container that you put stuff in. That kind of gives you a central location to configure your agents and monitor them. There's only 2 types of components in it, and it's very similar to the existing the DI container that's built into .NET. So there's services like your chat completion, but you can also just put logging or HTTP clients in there. And there's plugins, which are things that your AI uses to plan and do its work. So hopefully, if you go back and look at these diagrams after the coding demo, these will all sort of make a lot more sense. But you have your app, the user puts a prompt in it, the AI decides all this stuff for itself, right? Which functions do I need to use? How am I going to parse the responses and put all this stuff together before finally giving a response or doing actions for the user, right? Why semantic kernel? Same thing as REST APIs, essentially. Otherwise, you have to learn all these different interfaces and quirks of each individual service. Semantic kernel kind of unifies that. The LLMs that are compatible with semantic kernel have to support function calling, but I think they pretty much all do nowadays. And I'm going to try to finish this coding demo within 15 minutes here. Okay. Cool. So I've kind of chopped this up into steps here just to make it easier to read. Going to go ahead and put a breakpoint there and debug. But here's the first one here, creating the kernel. So all you do is it looks very similar to existing service collection. You say kernel.createBuilder. In this case, I've already created a free tier Azure OpenAI on Azure, which just gives me basically my own chat GPT to talk to with OpenAI 4.0 mini. So here's the endpoint, and I have an API key that I'm using. I have also decided to add console logging to my kernel, but that's all I did, right? Then I built my kernel, and I said, get the chat completion service out of it, since it's basically a DI container, right? I said, get required service, this guy. And then this is pretty much just like using ChatGPT or something, right? So we'll say, just invoke prompt async. I'm going to say, give me a list of weekly household tasks. It will be a little bit slower. I'm using 4.0 mini. I'm on free tier, right? I'm not getting like cream of the crop here, but this pretty much looks like a normal response from an LLM, right? Here's a list of household tasks. So that in itself is pretty cool, but not super interesting. It's the same as using an LLM, but now you got it in your code, right, to do stuff with. So we can do a few more interesting things. We have this thing called prompt templates, right? So I'm saying, what are some fun things to do if I'm visiting city, but I've got this city parameter here now, right? So I create a create function from prompt on the kernel. It's really wanting to give me documentation. And goodness gracious. And I give it the prompt. I'm going to say the city here is San Antonio. So obviously these 2 parameter names have to match up. But if I go ahead and invoke that, see what it gives me here. And let's see. The Alamo Riverwalk is actually a pretty good list. Cathedral, San Fernando Cathedral, Pearl Brewery. Yeah. So it gave me, here's some things to do in San Antonio, which by my judging, since I live here, is a pretty good list. You can call invoke async on the function object itself or on the kernel. It's the exact same thing. So since I already invoked it, I'm going to drag it down here. I don't want to invoke it again. Okay. There's this thing called handlebars prompt templates. This is not a thing that Semantic Kernel invented. Handlebars is its own thing. It existed already. It's this XML type template. So the nice thing about these, I've just made a string of it here, but you can save these as files in your project if you have these kinds of things you use a lot, right? And I've kind of given, this is an example of me giving the LLM an example first. So I'm giving it a system prompt saying instructions, identify the from and to destination and dates from the user's request. And then this example user has said, can you give me a list of flights from Seattle to Tokyo? I want to travel these dates. And then this example LLM has replied with this. So I'm saying, hey, this is how I want you to act. And then I say the real input is going to be from the user in this input parameter, which is going to be my handlebars input right here. So I'm saying I want to travel from May 18 to July 24th. I want to go to Norway for NDC Oslo, and I live in San Antonio. And then I'm going to say new kernel arguments, giving it the input of that string I just made. So very similar to the above example. It's just using this handlebars thing instead. I just throw all this stuff into a config object. Then I pass that config to this create function from prompt method they provide. And then I invoke async on that function object. So you can see now it kind of gave me, all right, I don't know if that's, I didn't check flights to see if that's going to be what I want, but it did spit me out a result in the format I wanted, right? So that's quite cool. Really, to make this useful, any LLM useful, we probably need chat history for context, right? So we can do that. We can do that with Semantic Kernel. We just create this here chat history object. So this history object has 3 types of messages you can add to it. I kind of went over this briefly earlier. You can add system messages, which is kind of like the initial how you want the LLM to behave. You can add user messages, which is what the user is asking the LLM. And then you can add assistant messages, which is how the LLM is responding. Okay. So I'm going to add a system messages to kick it off here. I'm going to say, you're an assistant, but respond kind of rudely and annoyed. Apologize after because it's just been kind of a rough week for you. And we'll see if that works. And I'm just putting this in a while true loop so the user can have a continuous conversation with it. So it's going to read my input now. So I'm just going to ask it, hey, how's it going? And yep, got my input. So I'm going to add a user message to the chat history now. Notice I don't have to add every single message to the history if I don't want to. I can manage it how I want. And then I call this get chat message contents async. And it returns these in chunks. So you have to iterate over them. I think these will probably always be in a single chunk. Yep. So, just another day. What do you want? Apologies if I'm a bit snappy. It's been a rough week for me, so it worked. I'm going to add now the LLM's response to my chat history with this add assistant message. And that's all working. So I don't want to stay in this while true loop forever. So I'm going to drag us out of here again. So this is really where the interesting stuff comes. These are plugins. This is kind of what makes your agent an agent. So I've just written a plain old C# class here called task management plugin. In real life, this would probably be hooked up, to a database or Jira or something. In this case, I just have a static list of, these are kind of like Jira tasks or something, right? So I've got, some titles, some descriptions, the status, if they're in progress or not, and the priority. So we've got high, critical, and medium on these. And we've got some pretty simple functions in this class. Get all tasks just returns a list of them. Get critical tasks just returns where the ones are critical. And then complete a task. So we take in an ID. It looks for it. If it doesn't find it, it just bails out. If it does find it, it sets it to completed, and then it returns that task if we want to do something else with it. And you'll also notice we have these attributes on them. So this is the kind of the important thing here. So LLMs, modern LLMs support this thing called function calling. Semantic kernel did not invent this. This is a thing that exists on them already. Basically, this is exactly what it's for. If you have deterministic code or something that you want your LLM to be able to call, you give it a name and an English name and an English description of what that function does and what it returns. And the LLM will plan for itself when it needs to call those things. So here's an example here. This is what semantic kernel is doing for you with those attributes, okay? So if you're using another library, you might have to make this JSON yourself, right? But here's a tool in the JSON, in the plain old JSON it creates. You can see it's got a name, get weather, it's got the description, and it's got a list of the stuff it takes in. It takes in a string, and it is required, and it's got what it spits out back at you. But rather than having to make this JSON, all we have to worry about are these little attributes here. So that's quite nice. Okay. So we've got our task management plugin. We add it to our kernel by saying .plugins, add from type, and giving it just the name of task management. We're going to invoke our complete task from here, but we're not going to call it in the code. We're going to have the LLM invoke it, okay? So all this complete task does, again, is set the status to completed, which is why I made this list public and static so we could peek at him in our watch. So to see if this guy worked, what we're going to say here is we're going to say kernel arguments with ID of 1, and then we're going to invoke async complete task. So what should happen is the task with the ID of 1 gets its status set to complete, because that's all our tool does. So right now, ID of 1 status is indeed in progress. Let's just invoke async our guy here, and it did get set to completed. So that's notable because we did not deterministically call that function, right? The LLM called it for us and ran it. So that's pretty cool. This is just a way to view. Here's the JSON that gets generated from your attributes. If you want to view it, you can do this JSON schema 2 string on them. Just kind of an aside, but cool to see. Also notable that this is not one tool with 3 functions in it. As far as the LLM is concerned, this is 3 separate tools, okay? Just because they're in the same class, because they're related, the LLM doesn't care. These are 3 separate tools with 3 separate JSONs. Okay. So let's put our chat history back in here. And I'll say, what are all of the critical tasks? That's all I'm giving it. It's hooked up to my tool. I'm not giving it any other info, though. I'm just saying, hey, LLM, can you tell me what all my critical tasks are? You can sort of give it some different behaviors of how it should plan to execute your tools. Here, I'm just telling it, hey, decide for yourself. Then I'm going to say, same thing as before, get my chat message completion content. It's going to get me my chunk. And let's see what it said. I got to get my chunk first. So it said, here are the critical tasks, fix login bug and fix UI. And it's sort of given me the details about them. So again, right, I did not tell it anything else. It made that plan for itself from the 3 tools I provided it, right? So let's do something slightly more interesting. Let's say where this probably would become useful is we have these tasks here. Maybe I have, I've got fix UI. I know that task is out there, but I don't remember the ID, but I need the ID to complete it. So I can say like, complete the fix UI task, because I know I did it, but I don't remember where it is. I don't want to go looking for it. And that's the only input I give the LLM. So let's add that user message, send it over to the LLM, see what it does. Kind of curious what the response will be since I didn't actually ask for a response. So, okay, it did give me something in English. It said, hey, it's been completed. Here's the updated details. But let's go look at our actual data and see if it did indeed do it, which I think was this third one here. So it did. So fix the UI not appearing is now completed, when initially it was in to do. So all I did was send the LLM an English prompt that said, hey, can you complete this fix UI task? I didn't even give it the ID, which is required to call the complete task tool. So from that little tiny English prompt, what the LLM just planned for itself, what it probably called this get all tasks, saw the fix UI task. It said, okay, here's the task. It's got an ID of 3. And then it called the complete task, passing in that ID of 3. So it planned all that for itself, just for my little message. So that's pretty cool. And that's basically the gist of semantic kernel. Really not very complicated. Kind of the sky's the limit is the limitation with this. Is just the ideas you can come up with, right? So if you can think of something cool, it won't actually be that hard to do with semantic kernel. I think the hard part is just thinking of something cool. So probably the important parts you want to do with your plugins are things you don't trust the LLM to do, like maybe financial calculations or math or like getting current weather data. The LLM won't know current weather, for instance. I don't think I showed the NuGet packages. So just real quick, it's just Microsoft Semantic Kernel. I had a few ones in there for Open API and handlebars. That's it. That's pretty much it. So close out here. I'm not going to go over all these, but Microsoft has kind of these 6 tenets for responsible AI usage that they try to hold themselves to and recommend you hold yourself to. If you want to go and look and deep dive into some of this stuff yourself, this is where I took most or all of the information in this talk from. In particular, these first 2 YouTube videos are fantastic. 3 Blue, 1 Brown has amazing visuals to explain how LLM works. And Andre Karpathy, this is a 1-hour video. He was a co-founder of OpenAI and former director of AI at Tesla. And he just has like multi-hour long videos on his YouTube channel for free. As far as I can tell, he's not selling anything, just explaining how they work. They're amazing. So go check those out if you want to learn a little bit more. That's it. You can wrap up. I will take questions if anyone has. I didn't see any in the chat.
I didn't see anything come through either. So if anyone has questions, feel free to pop them into the chat real quick or come off mute if you're comfortable. But while you're deciding if you're going to do that, I'll start closing us out here as well to get you out on time. So the recording will be published and the slides as well. They'll be emailed out to you here in the next day or so. And we'd love your feedback on this session. If you want to leave some feedback for Dan, feel free to do that. There should be a survey that pops up when you leave the session. And with that, thanks so much for joining and have a great day. We can hang on for a couple of minutes to see if there's any questions, but feel free to pop off mute if you like.
I think everyone was just stunned by the presentation. It was just so well explained they didn't have any questions.
Exactly.
I think that was it.
All right. I'm not seeing anything else come through. So thanks everybody so much for attending today, and we hope to see you again soon.